Hey guys, sorry I'm not able to be there today, but I've got the notes recorded, so you're not going to miss a day. I'm sure you're happy about that. But here's the opener. Today we're going to talk about nonlinear inequalities. So that just means inequalities that aren't lines. We know how to graph inequalities that are lines. Remember, what you're going to do is you're going to graph that border line. You use the broken or dashed line to indicate that the border is not included in your solution. So in other words, it's the greater than or the less than signs. You're going to use the solid line if it's less than or equal to, or greater than or equal to, meaning that it's inclusive, meaning that it includes the borderline. And then you test a point, and you're going to shade the side that's true. So pause the video and do these 4 as an opener, just reviewing how to graph linear inequalities. Okay, so let's go over these. So it's in standard form. So the best way to do standard form, especially if the left-hand side are factors of the right, so your A and B are factors of C, is to find the intercepts. So that means you set your x equal to 0, and then you've got 3y is greater than or equal to -6, or y. And since we're just looking for the intercepts, we can make this an equal sign. So y is equal to -2. So my first point we have is 0, -2. The second thing we can do is set y equal to 0, leaving us with 2x equals -6 or x equals -3. So we've got -3, 0. I can connect the dots. 1, 2. And extend the line. We're going to use a solid line in this case because of the inequality greater than or equal to. It means that the line is included. Then we test a point. As long as 0, 0 is not on the line, we test 0, 0. That would make 0 plus 0 is greater than or equal to -6. That's true. So the point at 0, 0 is true. It is a solution. So every point over on this side will be true. So we shade that side, indicating that any point on this side is going to be a solution. If it were false, we would have shaded the other side, but since it's true, everything on that side makes the inequality true. We're going to do the same thing here. This is just in slope-intercept form. So we take my intercept from the -1, and then I graph up 1, 2, 3 over 2. Same thing, up 3 over 2, up 3 over 2, up 3 over 2. Now this one is 1, 2, 3 over 2. Sorry, I'm doing the other side. 1, 2, 3 over 2. 1, 2, 3 over 2. This time we're going to use the broken line. The broken line indicates that any point on the line is not going to work. So we don't want to include those. And there's my broken line. 0, 0 is not on the line, so I can still use 0, 0. So 0 for the y is greater than 3 over 2 times 0 is just 0 minus 1, or 0 is greater than -1. This again is true. So my 0, 0 is true. And that indicates that this side of the line contains all of the solutions. X is greater than or equal to 4 is still a linear inequality. X is equal to 4 is a vertical line. no matter what your y is, your x is equal to 4. So you get all of these points here that go together and make a line. We're going to use a solid line because the 4 is going to be included. I'm going to label this just so it looks different than our y-axis. If I test a point, 0 is greater than or equal to 4. That's not true. So this point here would be false, and we want to shade the other side. Last one of the opener, y is less than 2. Very similarly, y is 2 regardless of the x, which means I've got a line that's horizontal. I'm going to use a dotted line here because it's less than. It shows that the line is not included in our solution. Now you can also do this logically. If y is less than 2, it means all the points below. So we can shade everything below the dotted line. If you were to test a point, again, testing 0, 0, 0 is less than 2. That's true. So if that's true, that's on the side that's included. So that's just a quick review showing that you already know how to do these. So the same process is going to apply when we are graphing nonlinear inequalities. So if we graph an inequality with a parabola or an absolute value v, what you're going to do is you're going to graph that border. You use a dashed line or a broken line if it's greater than or if it's less than. That means it's excluding the border. Use the solid line if it's greater than or equal to, or less than or equal to. And that just means that you include the border line in your solution. Test a value that's not on the graph. Typically 0, 0 is the easiest. If it's not, if it's on the line, then you pick a different point. And then you're going to shade the side that's true. So let's take a look at graphing this first inequality. It's a cubic, so that's nonlinear. We can graph this using our transformations. So a regular cubic would mean plug in 0, you get 0, plug in 1, 1 times 1 times 1 gives you 1, 2 times 2 times 2 is 8, 2, 3, 4, 5, 6, 7, 8. 1, 1, 2, 3, 4, 5, 6, 7, 8. So the graph of a plane cubic, so y equals x cubed, looks something like this. This 4 means we're going to move it to the right 4. This 2 means we're going to move it down 2. So this 0 is over 1, 2, 3, 4, down 2. And now I can graph the typical y equals x cubed from here. So -1, -1, -2, 1, 2, 3, 4, 5, 6, 7, 8. Over 1 up 1 cubed, over 2 up 2 cubed, 3, 4, 5, 6, 7, 8. Of course it's in there. I'm just going to clean this up a little bit. I'm also going to erase my cubic parent function because we don't need it anymore. And you can see that my graph is here. Not the best, but there it is. I use the solid line because it's greater than or equal to. And I'm going to test a point. 0, greater than or equal to 0 minus 4 cubed minus 2. 0 is greater than or equal to -4 times -4 times -4 gives me -64. minus 2. 0 is greater than or equal to negative 68, or sorry, 66. So that means the 0, 0 is true. I shade on the side that's true. Now, you could also look at this logically. It's asking for the y's that are bigger. It says y is greater than or equal to. So, getting a little distracted by my shading, sorry. So you can, any y that's bigger than this y here is going to be this side. Any y that's bigger goes up this way. So you can also see it logically there. We can do the same thing with absolute values. I don't like this form, so you can put it in a form that that's more easily recognizable. Remember, ax minus h plus k gives you a vertex at h and k. The slopes of my lines are going to be at a and negative a. We just know that from the absolute value form and our rules for transformations. So I'm going to put this in that form. So y is greater than negative absolute value of x plus 2 plus the 3. So all I did was move the 3 to the other side. And now I can see that I'm going to have a vertex at negative 2, positive 3. I'm going to have slopes of negative 1 and positive 1. Because this is a negative, remember that's a reflection across your x-axis. Reflect across the x. All that means is it's upside down. So my v is going to be upside down. So knowing this, I can put my graph in. Vertex at negative 2, positive 3. I have slopes of 1 and negative 1. Put a reference point out here. A reference point over here. And I can put in my dotted line. Again, it's a broken line because it is greater than symbol. It means that the border is not included. Again, I can look at this logically and I can see that it's asking for y's that are above my graph. But I can always test 0, 0 is not on the border. So I can test 0, 0. If I start with y is greater than negative x plus 2 plus 3, I get 0 is greater than negative absolute value of 2 plus 3. So the absolute value of 2 is just 2, which gives me negative 2 plus 3, or 0 is greater than 1. That is false. So inside here is false, and you can see that what you're going to do is shade above the line. I hope you're all good with this. So that's the basic way to graph nonlinear inequalities. You might also be asked to solve them algebraically. And depending on what they are, you may have to go into multiple cases. If you remember, we have multiple cases with absolute values because we have different situations. If a is greater than 0, the absolute value, let's try that again. The absolute value of a is going to be equal to a. If a is less than 0, that means the absolute value of a is going to be equal to the opposite of a. Sometimes that's easier to look at with numbers. So if we say, if a is equal to 2, we know that that's greater than 0. The absolute value of 2 is equal to 2. If a equals, let's say, -4, the -4 is less than 0, so we know that the absolute value of -4 is equal to the opposite of -4, which is +4. So anyway, this is how we have to deal with two cases. So in graphing the inequality, the absolute value of x minus 2 minus 5 is less than 4, I'm going to look at two cases. The first case is the case in which x minus 2 is negative. So what's inside the absolute value is negative. So in order for what's inside the absolute value to be negative, that means that x is going to be less than 2. So when x is less than 2, what's inside the absolute value is negative. Remember from over in this case, if the absolute value, if a is less than 0, so what's inside is less than 0, the absolute value is going to be equal to the opposite. So I take my inequality, and instead of using the absolute value of x minus 2, I'm going to analyze the opposite of what's inside. So now I just solve it as normal. So negative x minus 2, I'm going to add that 5 to the other side, makes it less than 9. I'm going to divide by -1. This gives me my x minus 2. Remember, dividing by a negative makes us flip the inequality sign. And we've got the -9 there. Then we add 2 to both sides. So x is greater than -7. Now, this was my situation. So x is less than 2. And my result is x is greater than -7. Both of these guys have to be true. So we can put these together. What this means is that x is less than 2 and x is greater than -7. Oops. -7. So we can put these together since it's an and, as long as the numbers increase from left to right. So the -7 is less than the 2. Make sure that all of the inequality signs point towards the left. So what we get is -7 is less than x, which is less than 2. My second case is the other side, where x minus 2 is greater than 0. We also have to include 0 because it could be 0, so I'm going to include it on the positive side. So when it's positive, remember then we have this rule here. If a is greater than 0, then the absolute value of a is going to be equal to a. So it looks just like what's inside. So we take my inequality. Instead of using the absolute value, I'm going to just make what's inside x minus 2 minus 5 is less than 4. So adding the 5 to both sides, we get x minus 2 is less than 9. And x is less than 11. So that's going to be important, as well as the situation that makes what's inside positive. That means that x is greater than or equal to +2. So now both of these guys are connected. So what we get is x is greater than or equal to 2 and x is less than 11. So 2 is less than or equal to my x, which is less than 11. Now, between the two cases is an or. because your value inside the absolute value can be either positive or negative. That means between the two cases, we have an or. So this is my solution here. Now, if you look at this, you can see that you can put them together. You can see it on a number line. -7. Let's put 0 here. Let's put 11 here. And then we've got another critical value at 2. So my first inequality goes from my -7 to +2. My second inequality goes from +2, but with a solid dot, to the 11. So we can actually combine these into -7 is less than x is less than 11. And that's my solution. The last type of problem that you might get is testing whether points are solutions to an inequality. And this is what you do when you're trying to test a solution against anything, is all you do is you plug it in and see if it works. So we would take the first one, 3, -4. What that means is your x is equal to 3, your y is equal to 4. So I get 4 is less than or equal to, oops, I left off negative, didn't I? Y is equal to -4. So x minus 2, so we get 3 minus 2 squared minus 3. So -4 is less than or equal to 1 squared minus 3. So -4 is less than or equal to -2. Is that true or is that false? -4 is less than or equal to -2. This is true, which means 3, -4 is a solution. Testing the next one, 4, 7. This means my x is equal to 4 and my y is equal to 7. I'm going to replace each of the variables with parentheses. This helps me not lose negatives. So y was 7, x was 4. So 7 is less than or equal to 4 minus 2 is 2 squared minus 3. So 7 is less than or equal to 4 minus 3, or 1. Now, this is not true. 7 is not less than or equal to 1, so this is false. And what that means is that 4, 7 is not a solution. Uh, 1, 1. Again, I'm going to replace the variable x and y with the values that are given to me in the point. So we get 1 is less than or equal to 1 minus 2 is -1 squared minus 3. So 1 is less than or equal to 1 minus 3, or 1 is less than or equal to -2. Again, this is false. So what that means is 1, 1 is not a solution. Last one, -1, +6. Again, y is less than or equal to x minus 2 squared minus 3. Plugging in the 6 for the y, -1 for the x. 6 is less than or equal to -1 minus 2 gives me -3. Square that is 9. So 6 is less than or equal to 6. This one is true. It's actually on the borderline. What that tells me is that -1, +6 is a solution. All right, if you give me a second, I get your homework right here, or your classwork, because you should have time to get this finished while you're in class. It is 1 through 12 all. And 13 and 15. And then 21 through 31 odd. And then 33, 35, 37. And that's section 3. I can't remember. Hold on. 3. And this will all be in Google Classroom. Again, sorry you guys that I'm out. I will see you on Monday. Have a great homecoming game and dance, and I'll see you Monday.